So, hello and welcome back to Calculus 2. We have section 8.5 with another 4 tests. We have ratio test, root test, direct and limit comparison tests. So the ratio test is one of the most important tests, especially that's the one that we are going to use for power series, and it's used later in mathematics as well. So really the one that you should know. So for ratio test, we'll say that let summation AK or AN, whatever, be an infinite series with positive terms all right, so that's the let part. We have summation of, oh sorry, not summation, limit of absolute AK plus 1 divided by AK as K goes to infinity so this can have 3 outcomes. So if the answer for this is less or equal than 1, sorry, not equal. If it's less than 1, it converges. If it's more than 1, it diverges. And if it's equal to 1, inconclusive. So these are the 3 possibilities. And it's a very simple test to do. You shovel some algebra, and then you do the limit. And that's that. Now, what's important is, and I need to write this as well, this is the only test that works with factorials. Now, we haven't talked about factorials much, but we will be. Ratio test solves factorial problems. All right, so that's another thing. Now this factorial will have to address that. So let's first take a look at the ratio test. Clearly, ratio tests should solve other problems that we already covered. But this is mainly developed for the problems that have mixed types of functions. For instance, if I look at the problem, say n cubed over 3 to the n, as n goes, let's say, from 1 to infinity, right? You take a look at this series. The numerator is polynomial, right? It's n cubed. And the denominator is exponential. So in some sense, you have this battle between the P series and the geometric series, with this problem being both at the same time. That's no bueno, right? You can't use one or the other because they're both present. So what do? Well, the answer to this is ratio test. So ratio test is good for factorial problems, but it's also good and is used for any time when you have mixed types of functions, right? So that's that. So now, the way this works is you go and you make an or ak on a side, which is n cubed over 3 to the n, and then you do n plus 1, because you need that for the limit. n plus 1 would be n plus 1 cubed divided by 3 to the n plus 1. So every n is replaced by n plus 1. If n was 7, then it will be 8. Right? That's the next one. So now you run the limit. You have the limit. N goes to infinity, or k. Guys, absolute value. You have to put absolute value there. It's not there for decoration. You have an plus 1, which is n plus 1 cubed divided by 3 to the n plus 1, divided by the original n cubed over 3 to the n. You have double fractions, so deal with that. All right, n2 goes to infinity. We have our n plus 1 cubed divided by 3 to the n plus 1 divided by n cubed over 3 to the n, all of this in absolute values. Now, division of fractions changes into multiplication when you swap, right, switch the, flip the second fraction. So we have n plus 1 cubed over 3 to the n plus 1 times 3 to the n over n cubed. So now you have to take this limit. Well, the great thing here is that you can break this into 3 times 3 to the n. Because, right, 3 to the first power times 3 to the n is 3 to the n plus 1. So, limit, n goes to infinity. We have our n plus 1 to the cube divided by 3 times 3 to the n times 3 to the n over n cubed. And you see that 3 to the n cancels. Yay! 3 to the n cancels, leaving us with limit n goes to infinity, absolute value of n plus 1 cubed divided by 3 to the n cubed. Now, if you know your limits, you see that this is n cubed divided by n cubed. The rest of the terms will go to 0. So what you have here is 1/3 as the answer. That is less than 1. So we have convergence by ratio test. Now, students generally write the first setup and then jump into this step and then here. So, with practice you will be cutting out a lot of these unnecessary steps in between. But as I said, when you're learning for the first time, it's good to see everything. So ratio test is good when you have mixed functions. And you run those functions through limits. It will land in one of the 3 cases, hopefully not the third one. If it lands into inconclusive, you have to use something else. Then, right, it's good luck. If it's less than 1, we got a 1/3. Then it's convergent. If it's more than 1, it's divergent. Let's take a look at another one of these. So say you have summation of let's go with e to the n times n to the negative n from 1 to infinity. So, yeah. What do we actually have? Well, it's good to write this, use algebra, to write this as e to the n over n to the n. Now, if you write this as e to the n, everything to the n, and try to use geometric series, you can't. because your R cannot contain n in its right, because it has to be a finite value for you to make the distinction whether it's from -1 to 1 or not. So you can't use geometric series. I can write here on the side summation e to the n, everything to the n, and then just cross it out. It's like don't do that, right? So what you have here, these are different functions. This is the function that I call the boss function. Yes, the boss function. This is the boss function because it has the fastest growth rate from basic functions. Anything else is slower than this thing, if it's a basic function. Sure, I can make this faster if I go and then put a square on top or something. Sure, I'm making it faster, right? But it's faster than the square root, faster than the polynomial, faster than log, faster than exponential, faster than even the factorial, which we didn't cover yet. So this is the fastest in our realm of Calc2. So now we are going to use a ratio test because these two functions are not the same type of a function. This is not exponential function. So even though there is n in exponent. So we have to use ratio test. So we send n to infinity. And I have e to the n, and then I have e to the n plus 1 over n plus 1 raised to the n plus 1, right? That's what we have. So now let's see. We have e to the n plus 1 divided by n plus 1 to the n plus 1. And then immediately, as you can see, I'm skipping a lot of these steps. I'm writing down the original problem, but I'm writing it as a multiplication and flipped. So in the next step, I do the peeling, right? It's e times e to the n over n plus 1 to the n, and then n plus 1. And then times n to the n over e to the n. So now what happens is, well, limit n goes to infinity. E to the n drops. And what we have is e times n to the n divided by n plus 1 to the n. So now we have to take this limit. So we shifted now the problem into this, and I can go and say that if you know your properties of limits, obviously, you have your limit n goes to infinity of e over n plus 1 times the limit n goes to infinity of n to the n over n plus 1 to the n. So if you know your limits, right, you have this. This is further limit n goes to infinity of e to the n over n plus 1 times, now this exponent n, you can push the limit n goes to infinity of n over n plus 1 and have everything raised to the n. So these are the basic properties of limits that if you don't know, you can't play the game. I'm sorry, right? You have to know the rules to play the game. And I told you that on the first day, Chapter 8 is going to be heavy on limits. Learn the properties, learn especially section 2.4, right, which is limits at infinity, which is what all of them are, n goes to infinity. So now, the first limit is 0. So this whole thing over here is a big fat 0 times, and the second limit is going to be 1 raised to the n. Oh, sorry, you can't do this. Sorry, you can't do this. This has to remain like this. There we go. It has to remain like this. You can, but if there was any exponent like 3 or 7 or whatever, then yes, you can bring it, but you still have the limit there. So now what you do here is you have to do the long division on the side. For this part, we have n plus 1 divided into n, goes once. 1 times n plus 1 is n plus 1. When you subtract, these guys cancel, and you just get negative 1, so minus 1 over n. So this becomes limit n goes to infinity of 1 minus 1 over n to the n. There we go, much better. So now the 0 times, now over here you split this into two limits. Limit of 1 is 1 minus, oh no, what?
Wait, anything times 0 is 0.
Anything?
I don't know, someone for each other.
Anything times 0 is 0?
Why is it doing 0?
It could be 3/4. Right? L'Hopital's rule, we learned that it can be 3/4. We do not play with fire that way. I'm sorry.
Why is 0?
So the trick that we can use over here is I can put the negative at 1 and put a plus over there. So now this is the form of e to the negative 1. So now you have 0 times 1 over e, and now it's 0. Less than 1. Convergent by ratio test. Yay. Yeah, the limits tend to be now fun. Let's talk about factorials so that we can finish off. So talk about factorials. Notation is n with the exclamation point at the back. This is read as n factorial. It's not n, it's n factorial. All right, it's n factorial. There's no need for excitement. The meaning of this. The meaning of this is n factorial is equal to 1 times 2 times 3 times 4 times dot 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 times n minus 2 times n minus 1 times n. So you are to multiply all of the integers up to number n. So what is 5 factorial? 5 factorial is 1 times 2 times 3 times 4 times 5 equaling to 120. I believe that your calculator, which runs out of memory, these numbers pick up values extremely quickly. They go all the way to, they go into thousands very quickly. So let me see, the factorial button is under math, and then you go to probability. So when you go to math button and you use the right arrow to move to PRB, number 4 is a factorial. So let me see, 70, math, probability 4, 70 overflow. Okay, so it can do 70. Let's see, 69. Can it compute math? Because it's just on how much memory these things. These calculators are ancient, obviously. So this is from, yeah, it can compute 69 factorial at 1.7 times 10 to the 98.
This one gives up because it can't display to the 100.
Yeah. So you see that these values, guys, for factorials, they grow very fast, right? So factorial is very simply put just 1 times 2 times 3 times 4, and then you end whatever the factorial is. Now, we are going to need one very important property of factorials to solve these problems, and that is peeling off a factorial. So 5 factorial is actually 4 factorial times 5. Does it make sense? Because 4 factorial will have 1 times 2 times 3 times 4, and then times 5. Make sense? So because of that, we are able to write the formula, and I'll write this in red because it's important. N plus 1 factorial is n factorial times n plus 1. So that n plus 1 is the next term. So n factorial contains all of the terms that you have, and then times n plus 1, which is the next one, to create n plus 1 factorial. So now what is the n plus 1 factorial? I'm just going to write it over here on the side. It's 1 times 2 times 3 times 4 times dot 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 times n minus 1 times n plus 1, right? So that's what n plus 1 factorial is. And you see that if you take this much, that's actually n factorial times the n plus 1 extra. So we are going to need this to solve our ratio problems now. Factorials are important, obviously, for your computer science and all that stuff. So you have to be able to work with these things. So now I'm going to have a series that is going to be n to 100 divided by n factorial, starting at 1 going to infinity. So now, you see, students that don't want to learn, they use the intuition, they get it wrong, and rightfully so, right? So, right, what can you do? Now, those of you who want to learn, you memorize the conditions and conclusions of the ratio test. You also remember that if you see a factorial, it's a ratio test. Because factorials do not share the algebra with others, so it's you can't use any of the other tests. When you see a factorial, it's ratio or go home, right? So now you have this situation where you have your an to be n to 100 over n factorial, and an plus 1 is n plus 1 to 100 divided by n plus 1 factorial. And this is where your formula n plus 1 kicks in, right? Because you will have to peel off that n plus 1 term, and then the n factorial will cancel with the other n factorial. All right, ratio. We have a limit. N goes to infinity. We have our n plus 1, so that's going to be n plus 1 to the 100 divided by n plus 1 factorial times n factorial over n over 100, right? So I took that division already, and I wrote it in a linear fashion, and then I swapped it into multiplication. So I did all of those preliminary steps in one, just skipped a whole bunch of these things. Limit n goes to infinity. Now we do the peeling. N plus 1 to 100, you can't do anything for that, but in denominator you get to put n plus 1 outside and have n factorial. Times n factorial over n to 100, and this is where n factorial dies. So we have the limit n goes to infinity of n plus 1 to the 100 divided by n plus 1 times n to 100. Well,
Will it be n plus 1 to the 99?
yes, that's the next. So now okay, it's fine, yeah. So now you can either cancel one of these n plus 1s, or you can argue that the order of the exponent on the top is 100 and the order of the exponent of n on the bottom is 101. Since the bottom has the bigger exponent, the limit goes to 0. Or you can cancel, as you said, which is n goes to infinity, and it becomes n plus 1 to the 99 over n to 100. Again, n on top has 99, n on the bottom has 100, so again, this is equal to 0. Less than 1 converges by ratio test.
I like that.
So what I'm going to challenge you with as you are leaving is to pay attention and see the expansions and cancellations and things that you can, like peeling off terms for 2n factorial, 2n factorial, 2 plus n, I mean n plus 2 factorial, and you know, see what they expand, right? Play with these, write them out, see what they expand into and the way they work, because these guys are coming up. More advanced problems that we are going to work with will have 2n, that's only even factorials, right? Or only odd factorial numbers and so on, and what they give you at the end and how to cancel. That's most of the confusion, right? Happens when you have these kind of things. So tomorrow we are going to do the rest of chapter. We have 4 tests left, root, comparison tests, and alternating. And then we're going to start chapter 9. We will finish chapter 9 this week. We have, and then we should also talk about the exam tomorrow, if you want to have and when you want to have it, because next week on Thursday is the final. Let me stand here and repeat this. The final is the next Thursday. I will see you 6 times. That's it. I will see you 6 times. 3 times this week, 3 times next week, and then when you see me the 7th time is the final. Also, when your project is due on that day as well. I haven't seen a single turkey. I haven't seen a single proposal. Is this any good? Right, that I can butcher it and say, terrible, bring it back to the drawing board, right, so that you can make it be worthwhile and awesome.